Welcome. Now I'm going to start that next name reactions related to the carbocations. Name is Backman rearrangement. I think this is the ninth number of name reactions. That is Backman rearrangement. So in this name reactions, what is there that maximum times here what is given? The oxime is given to you, oximes, and that oximes that any acid group is there, H plus from any acids, or it may be given that POCl3, or it may be that PCl5, or it may be that SOCl2. So any of this will given, then this oxime is converted to the amide groups. Okay, acid that in the sense like H2SO4, HCl, that type of groups are there. So if that is given, then that is converted to the amides. So this type of rearrangement, this type of reactions is known as the Backman rearrangement. Okay, so oxime in the sense that is here, let's say R, and this is C, and this is R dash, and what we have there N, and here we have that OH. So this is the oxygen. Okay, this is the oxygen, and here we will have that any acid groups, H plus, or any acids, or this types of POCl3. This things is given. Then we will get that amide groups, that is RCO and H2, or it may be sometimes RCO and R. This type of groups you will get. Okay, so this is known as that Backman rearrangement. How this will happen, that I am going to explain that. We will look the mechanisms and detail about of it. Okay, and sometimes instead of giving oximes, what they will give, that they wants to make this oxime. So how will you make this oxime? So they will give any ketone groups or any aldehyde groups. Okay, and what they will give, that NH2OH. Okay, now from this, from this we will make this oxime. So this is the how the synthesis of oxime. So sometimes what will they give, that either they will give ketones or aldehyde groups, and they will give this one NH2OH. Then we will get that oximes. Okay, so what they will give, like this they will give, and secondly they will give that acid groups, H plus. Then we will also from here also we will get that amide groups. How it will happen, that here let's say if I do that NH2OH, then what happened, that here water will be released. Okay, so here what that this O and this H will release. So what water is going to release, so what will get here, R CON, this N, and then this OH, then this is the H. Okay, this what we will get here. Now after that, if you get that H plus, then we will get that amide groups, that is. Okay, so like this they will give either sometimes the maximum times what they will give, that they will give this oximes, and they will give this any H plus or any acid, or this one they will give, and they will ask to do these reactions. Or sometimes if they want to prepare the oxime, then they will give ketones or aldehydes, and they will give NH2OH. From that we will prepare that oximes, then H plus, then we will going to get the amide. Okay, now how this mechanism it will happen. So let's discuss about of that mechanisms, how the mechanism will proceed. So mechanism is, let's say we have these groups. I am directly preparing from that oximes, and OH is there, and here H is there. Okay, so from here how will you make that? So H plus is there. Then what will do that? Here lone pair is there. So this lone pair will attack to this proton. So this is going to be that R C double bond N, and this is going to be OH, and this is the H, and here we have that positive charge, and here we have that H. Now what will happen? Water will release. This water will release. So what we will get? This R C double bond N. This is going to be a positive charge, and here we have that hydrogens. Okay. Now what we are going to do that? This water we have released. So water is there. Okay. No. So now what will happen that we will do the rearrangement. Okay. That means that here migratory aptitude we will look at, which will do the migratory aptitude. The group will shift. Okay. So here migratory aptitude. So which is migratory aptitude? First is hydrogen, then R groups means R will be shift here. Okay. Nucleophile is also there, but this migratory aptitude will be do faster than that living group, that nucleophile. Okay, then so this will be shift here. So what we'll get now? This RC double bond N, and here we have H. Okay, here we have the positive charge. Now the nucleophile will attack. Means that we have water in the nucleophile. So this is going to attack to this electrophilic center. So what we'll get here? R C, this is double bond N, H, and here we have that water. This is positive charge. So this is going to release here. So what we'll get now? R C double bond N, H, and this is going to be the OH. Okay. And then now what will happen? Rearrangement. So now that tautomerism will happen. Tautomerisms. It means this hydrogen here, this is there. So this is going to shift here, and this is going to shift here. So what will happen? That R C, this will become N minus because that has shifted here. Here H is there, and here we have that double bond O, and H proton is there. So this is attacked to these protons. What will get now? R C double bond O, and that proton, so NH2. So what is this? This is the amide group. Okay. So what we get that from these oxygens we get the amide groups if H plus is there. Now that if instead of H plus, if PCl5 is there, for that also we see that let's say this R C double bond N and OH, this is the oxygen. Let's say there hydrogen is there. Now if we have that PCl5, okay, so that is, then what will happen here? The same things, this lone pair here, that Backman d orbitals are there, so this will going to attack here. Okay, and what will get now? This R C, and this is H, here double bond N, and this O, here H, and this will attack to the P, and whenever it attack, one chlorine will leave. So this is chlorine, this is chlorine, this is chlorine, and this is chlorine. Okay, and this is going to get the positive charge because lone pair has a give. So now this is going to like this. Okay, after that R C double bond N, this is going to be H, and this is going to be the O, and here lone pair is there, then P, Cl, 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 and Cl. So now we know that P loves oxygen. So P and O bond is very strong bond. Okay, so what happened that this will give here, and one will be released here, minus Cl. So what will get that? R C double bond N, and H, here O, this is double bond of P. Okay, this is again going to get the positive charge, and here we have that Cl, Cl, and Cl. So what will happen that since P O bond is strong, so this will be released here. So what will get that ultimate the same things we are getting, that is N here positive charge, here we have that hydrogen again. So this, so rearrangement will happen. So migratory aptitude, that is H is greater than R groups, so this is going to be shift here. That's what we get the same things, that is going to be N and this is going to be H, and here positive charge. So now previously what that water was the in the nucleophile, but here Cl minus is there, Cl minus, and water is also there, but what nucleophile character of chlorine is more because negative charge is there, so chlorine will attack now, not water. Okay, so that is going to be R A double bond NH, and this here we are going to get the chlorine. Okay, so okay, after that anything. So it will remain as here, and that amide groups. Mhm. No, water will attack, so that otherwise you will not get the amide groups. Okay, here water will attack, so that this and this is after that this one will get, water will attack, otherwise then we will not get that amide groups. So RC, that is going to be that N and H2, and this is going to be the double bond. Okay, so water will attack. If nuclear the Cl minus will attack, then we will not get that amide groups. Okay, so that's the what the rearrangement will happen, and this type of rearrangement is called the Backman rearrangement. But all these times we don't need to do these mechanisms. What we do that, we'll remember about of that shortcuts. So what is the shortcut? Shortcut is, so that says we have that maximum times they will give that oxygen. Okay, that means this is N, and here we have that OH, and let's say here we have that hydrogen. Now if you give that H plus, okay, that is from any acids, then what will happen? Now simply what will do that, convert this C double bond N, this is what we will do, this carbon, this what here this C double bond N, this is convert into the this CO groups. Okay, after that we will look that which has the more migratory groups. So here migratory aptitude will be checked. First convert this one into this, then check that migratory aptitude. So here H is greater than R, so in between C and H, NH will come. Okay, here C H is more than that R, H is more migratory aptitude than R, so that CO, then N will comes in between this and this CO groups. Okay, it means this, and here we have that NH. Okay, here we have that NH, and here we have that R, and this hydrogen is there, so that hydrogen again will come. Okay, so we understand that. It means whenever that group is there, let's say this is RCO and H is there, and now you have that H plus acids, then what we will do that first, sorry, this is the oxygen groups RCNOH, and H is there. First our work is to convert this CO. So first work, okay, step 1, what we will do, convert C double bond N OH, this one, into CO. Okay, this is the first one, and the step 2, what will do that, in between more migratory aptitude, and we have already converted this into CO, and CO. Okay, NH, insert NH. Okay, these are the two steps we will follow of the shortcut. Okay, this is about of that shortcut. So what I will do first, I will convert this into the double bond of CNOH. I will convert into the double bond of. Then now I will look that migratory aptitude, which is the more migratory aptitude H. So in between the CO and H, I will insert that NH groups. Okay, and here H is there, and this R will be remain as it is. So this is actually what this is going to be, that RCO NH2. So we get that amide group. Okay, so this is the we don't need to do all the times the mechanisms. We simply do this, then we will get one. Okay, and remember that whenever we are forming this carbocation, these carbocations, or we can write that conditions for Backman rearrangement. Okay, carbocations form should be 1 degree or 2 degree. Okay, carbocation form should be 1 degree or 2 degree. Then only it will go through the Backman rearrangement. Okay, and if it is 1 degree carbocations, sorry, if carbocation form is 3 degree carbocations, then that will go to the Backman fragmentations. That will not go by Backman rearrangement, that will go by Backman fragmentations. Okay, so that we will see that whenever you are discussing the examples, while solving examples, it will be more clear. So let's take the examples in this case. Okay, so see here in this example, if you notice this, so this first work is to either PCl5 or it may be H plus, anyone is given. First our work is to convert this NOH into CO groups. After that we will check that migratory aptitude. Okay, so now this is the 1 degree carbocations. After breaking, okay, this is the 3 degree, but after breaking what it will become? Okay, after this will break, then this is sorry, after this will break, this is become 2 degree carbocation. Okay, because if I let S, then this is going to be the 2 degree carbocations. Okay, so this is the 2 degree carbocation and this is the 1 degree carbocations. Okay, now what we will look that first our work is to convert this into CO groups. First our work is to convert this into CO groups, and this next what we will do that we will check that which is has the more migratory aptitude. So migratory aptitudes I have already explained that for alkyl groups, first 3 degree, then 2 degree, then 1 degree. So this is the 2 degrees. So here in between CO and the more migratory aptitude, insert NH. So here I will insert the NH. Okay, and remain everything is same. So after that we will make this bond. Okay, so this is the answers for these questions. Similarly, we will move to the next questions. Here also what you see that this is the any acids. So what we will look here, first our work is to convert this into the CO groups, and then we will look that migratory aptitude. So this is going to be the, after it will break, it will going to become 2 degree carbocations. Okay, and this is the 1 degree carbocations. So okay, so for Backman rearrangement this has to be either 1 degree or 2 degree. If it is 3 degree, then that is going to be a Backman second order rearrangement, or that is going to be fragmentation. Backman fragmentations will occur. After break, this is going to be 2 degree carbocation. So this is go through the Backman rearrangement. What will happen here? This is converted into CO, and in between that which is more migratory groups, then that CO and in between more migratory group insert NH groups. So what I'll do here, this, and so this is going to be CO and this is the more migratory group, so this is going to migrate. In between I will add that NH, okay, and this is going to be like this, and this is the methyl. So this is the final answers for this question. So likewise, we will solve that Backman rearrangement. So what we have to notice, convert this group into CO groups and insert that NH in between that CO and the more migratory aptitude groups. Like in bare villager oxidations, what we used to do that, there we will use to insert that O groups. There we will insert that oxygens in between the in between the CO and more migratory aptitudes. Okay. Now here also we are inserting that NH in between CO and more migratory aptitude. But here one more steps we are doing, that is we are adding, we are converting this NOH into the CO groups. Okay, that is that Backman rearrangement. Okay. So in this way we can solve that more questions regarding that Backman rearrangement. Okay. Now moving to that Backman fragmentations or second order Backman rearrangement. Here also everything is same, just that if carbon is 3 degree, if carbon is 3 degree, then this will go through the Backman fragmentations. Okay, it will not go to the second Backman rearrangement. This is the just I can say that second order of Backman rearrangement, means that update version of that Backman rearrangement. But that if 3 degree carbon is there, on that case it will not happen that Backman rearrangement, it will happen through that Backman fragmentations. Okay, and everything is same here also, that oxime is there, or here also the same manner whatever we have studied for Backman rearrangement, like from aldehyde or ketone is there, then NH2 is there, that we convert into oximes, and then H plus or POCl3, these are there, the same things is there. Then the if, but here what, if it is 3 degree carbon, if it is 3 degree carbon is forming, then it will not go by Backman rearrangement, but it will go by Backman fragmentations. So here we see that after it will break, this is going to be 3 degree carbon, and since 3 degree carbon is more stable, so it will not do that migratory aptitude. It will 3 degree carbon is stable, so it will remain as it is. So how these reactions will happen, let's see. Okay, so this, and here we have that C, here we have the double bond N, here we have that OH is there. So sorry, first what will happen, same things as that Backman rearrangement. Here N is there, here OH is there, and here CH3, here CH3. So first thing is the same as for Backman rearrangement. This is attached to this. So what we'll get here, okay, so this is going to be N and this is going to be OH2 positive charge. Here we will have that CH3, here we will have that CH3. So that water will leave here. Okay, so then what we'll get now, okay, so this is going to be that N positive charge, and here we have that CH3 and CH3. So after that, what is to do that for Backman rearrangement, that this migratory aptitude we used to see, but now we will not do this one because this is going to be the 3 degree carbon. So what will happen, it simply break it, then what you will get here, this is going to be C, this is double bond of N, here we have positive charge. Since it will break here, so here we will get a negative charge, and this is here CH3, and this is CH3, and this is going to get the positive charge, because bond means positive and negative. So if you break it, where electron gone, that is negative, where electron is absent, that is going to be positive. Okay, because this, whenever you break this, then this is going to positive, this is going to be negative. So that's what I did now, and we know that positive negative make bond. So what I will do here, this C triple bond of N. Okay, and this is going to be that C, and CH3 is there, and CH3 is there. Okay, so now what is that water is there? So that water will attack here. This is the positive charge, so this water will attack here. So what will get now? C triple bond N. This here we have that CH3, here we have that CH3, and here we have that water, means H and H. So that will be like this. So we will get here OH. Okay, so this is the final answers for this question. So that is going to be form a carbocations, and then that water will attack. Okay, now this is the case if H plus is given. Okay, now if it is POCl3, then that is going to be the product is little bit different. If it is a POCl3 or POCl5, then what will happen? The same things that will do here that I have already discussed, that this lone pair will give to that this, because this P is Cl, 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 Cl. So this is going to be give here, and this is going to be released. So what will get now? Okay, so this is going to be N, this is going to go this H. Okay, and this is going to be the P, Cl, 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 and Cl, because one has left. Okay, now this is going to be a positive charge. So what will happen that this is going to give here, and one chlorine again left. So minus L, then this is going to be like this. Okay, this is going to be N, and this is going to be the O, and here P, here Cl, Cl, and Cl. So this lone pair is there. So this again it will attack here. Okay. So what we will get now? This is going to be like this, and this is going to be N, and this O. Here we have that P, and we have C, C, Cl. So this is again going to get positive charge, and we know that P and oxygen is a very good bond. So this is going to left here. So what will get that same things we will get as that. Here we have that CH3, and here also we have that CH3. Okay, it is mentioned here CH3 is there. So again we are getting that here N positive charge. So now this is 3-degree carbon, so again it will break here. Then what will get now? So this is going to C, and here double bond N, here positive charge is there. So this is break, so here going negative, and here we have that CCS3, CCS3, and this is going to be positive charge. So now what will happen that positive negative make bond, they are going to be Cl. So now what happened that here Cl is there, and water is also there in the middle, but Cl minus is more nucleophile than water, so that Cl will attack here. Okay, so that is the difference between that and this. Here what will get now? C triple bond N, and this is going to be C, CS3, CS3, and this is going to be the Cl. So this is the final product for this question. So previously, but if acid is there on the time, water will come, but if POCl3, PCl5 is there, then Cl will come. This is the difference between that and here. What we get here in this case, water has come, this OH is there. Okay, if it is acid, and if it is PCl5, on that case what we get that Cl will be present here. Okay, so that is the difference between that and this. Now again in these questions we will solve this one. This is the last questions for this. So whenever 3-degree carbocation is there, on that time Backman rearrangement will not happen. What we will do that? Backman fragmentation we will do here. Okay, in this case PCl5 is there. Okay, so again that same things, CCl and CCl and CCl. So this OH will be going to give this vacant d orbital of PCl5. So that is going to be vacant orbital of phosphorus. So that is going to be like this. Here we have that methyl, and here we have N, and here OH, and this is going to be bond with the this phosphorus. Okay, here we have that Cl, Cl and Cl and Cl. Okay, one is already left. So now what will happen? This is going to be a positive charge, so this is going to leave here. The same things. Okay, so this is going to be that N, and this is going to be the O. Now this is going to be, and this is going to be Cl, and this is going to be Cl, Cl, and this is going to be Cl. So now what will happen? That here we have that methyl also. This is going to give here, and one is going to leave here. So what will get now? This is going to be N, and this is going to O, double bond of P. So here we have that Cl, here we have that Cl. Okay, now what will happen? This is going to again positive charge, and the PO bond is very good, so this is going to live here. After that, here, then this is going to be N positive charge. So now what will happen now? Since this is again the 3-degree carbon, after you break it, this is going to be 3-degree carbon, so this will be break. Okay, so this is going to be the 3-degree carbon, and here we have that negative charge and double bond and positive charge. So positive negative make bond. This is going to be Cl. Okay, now what will be there in the medium? Cl is there, so that Cl will be attacking to this one. So what will get now? Okay, so here and then here we will have the Cl, and here we have the C triple bond F. So now if you convert into that, this is how many rings? So count here. Let's say this is 1, this is 1, then this is 2, then this is 3, this is 4, this is 5. Okay, so 5-member ring. This is out of the ring. So 5-member ring I will 2, 3 and 5. And we have, okay, so this I convert into the 5-member ring, and this one it has this CH2 and this C triple bond N is there, and on that case of 3 I have here, and here I have that chlorine. Okay, now what we have seen that here base is given. See that here base is given. In this case base is given. So if base is given, then elimination chances is possible, because here we have that hydrogen, and base work is to abstract the proton, so it will abstract it, and this chlorine leaving group will leave. So what will get here? Here we have the double bonds, and here we have this methyl is there, and here we have that CH2 the triple bond F. So this is the final product for this questions. So likewise we will solve the questions related to Backman rearrangement and Backman fragmentations. Backman rearrangement and Backman fragmentation is same, only difference is that what we see that whenever you talk about of that Backman rearrangement, another is versus Backman fragmentations. Or this is also called that second order Backman rearrangement. Okay, so what is that? Here this is applicable for 1-degree carboguidance or 2-degree carboguidance. Okay, this is the important points. If it is 1 degree and 2 degree, and if it is 3-degree carboguidance, on that times the Backman rearrangement will convert into the Backman fragmentations. So if it is 1 degree and 2 degree, apply Backman rearrangement, and if it is 3-degree carboguidance, on the times apply Backman fragmentations. That is the difference between the Backman rearrangement and Backman fragmentations. Here also observed, the similarity is this is the difference, and similarity is everything is similarity. Okay, here Backman rearrangements, and here Backman fragmentations. What is that? Here also the same oxygen is there, and H plus will give, here also the oxygen and H plus. Okay, everything is same. And here also they will give that ketones, or they give that aldehydes, then they will give that NH2 OH. Here also the same things, ketones or aldehyde they will give that NH2 OH. After that they will give that S plus here. After that they will give that H plus. So same things, everything is same about a Backman fragmentations. Only difference is that here if it is 1 degree or 2 degree, then Backman rearrangement will do, and if it is 3 degree carbon, then Backman fragmentation will do. Okay, so today up to this, thank you. Next class we'll discuss more.